What if I told you that I once changed the equations of the universe because I was afraid of what they were telling me? What if I told you that I, Albert Einstein, added something to my own theory just to make reality fit what I wanted to believe? And what if I told you that this mistake, this thing I called my greatest blunder, might have been right all along? You see, when you discover that the universe is not what everyone thinks it is, you face a choice. Do you trust your mathematics even when it tells you something impossible? Or do you bend your equations to match what feels safe, what feels familiar? I made that choice once, and for years I regretted it. But today I want to tell you why I made that choice, what happened when I realized I was wrong, and why sometimes even our biggest mistakes can teach us the deepest truths about reality. This is not just a story about equations. This is a story about fear, about ego, about the courage it takes to admit you were wrong. And it is a story about how the universe has a way of surprising us, even when we think we understand everything. Let me take you back to the year 1915. I had just finished my greatest work, the general theory of relativity. For 10 years, I wrestled with the mathematics of gravity, space-time, and the fabric of reality itself. 10 long years of failed attempts, wrong turns, sleepless nights, and moments of despair when I thought I would never solve it. But finally, in November of 1915, I had my equations, beautiful equations, equations that described how matter bends space, how space tells matter how to move, how gravity is not a force pulling objects together but the curvature of the universe itself. I remember sitting at my desk, staring at those equations, feeling something I had never felt before, not just satisfaction, not just pride, but I had glimpsed something fundamental about reality. I had seen how the universe works at its deepest level. It was the greatest achievement of my life, but equations are not just symbols. On paper, they are windows into reality. They are predictions. They tell you what must happen, what cannot happen, and what the universe will do next. And when I looked through the window of my equations, carefully working through the mathematics to see what they predicted, I saw something deeply disturbing. The universe they described was not still. It was not peaceful. It was not eternal. My equations told me that the universe must be moving, either expanding outward, growing larger. With every passing moment, like a balloon being inflated or collapsing inward, shrinking down toward some catastrophic end, crushed by its own gravity. There was no middle ground, no stillness, no cosmic peace, no way for the universe to simply sit there unchanged forever, and this terrified me. Why? Because in 1917 everyone knew the universe was eternal and unchanging. This was not some fringe belief. This was the foundation of all cosmology. The stars had always been there. The galaxies, we thought, sat quietly in space, unmoving, like paintings hung in an infinite gallery. The universe had no beginning, no end, no story. It simply was eternal, unchanging, perfect. This was what every astronomer believed. Every physicist, every philosopher who had ever looked up at the night sky, even Isaac Newton, the great Newton, had assumed the universe was static. And now here I was with my new theory of gravity, and my equations were telling me something completely different, something that contradicted centuries of human understanding. So when my own equations told me the universe must be dynamic, must be changing, must be either expanding or collapsing, I faced a crisis. Should I trust the mathematics even though it contradicted everything humanity had ever known? Should I publish a theory that would make me look foolish, that would challenge the most basic assumptions about reality? Or should I find a way to fix it, to make my equations say what everyone already believed? I chose to fix it, and this is where my mistake began. I added something to my equations, a new term, a small adjustment. I called it the cosmological constant. In the language of mathematics, we write it with the Greek letter lambda. It looks innocent on paper, just one small symbol added to my field equations. But do not let the simplicity of the symbol fool you. Let me explain what it actually means and why I thought it would solve my problem. Imagine you are holding a spring. If you pull the spring apart, stretching it, it pulls back inward, trying to contract. If you squeeze the spring together, compressing it, it pushes outward, trying to expand. This is how springs work. They resist change. They have a natural state they want to return to. Now imagine that empty space itself, the vacuum of the universe, behaves like this spring, not space filled with matter, not space filled with energy, just empty space, the void between the stars. My cosmological constant represented a kind of pressure built into space itself, a repulsive force, an outward push that existed even in the complete absence of matter. Why did I add this? Let me explain the logic. Gravity pulls everything together. If the universe contains matter, and all matter has mass, and all mass creates gravity, then over time everything should be pulled inward. The universe should collapse. But if space itself pushes outward with just the right amount of force, then it can balance gravity perfectly. The inward pull of gravity and the outward push of the cosmological constant could cancel each other out exactly. The universe could stand still, eternal, unchanging, exactly as we all believed it should be. And so I published my solution in 1917. I took my beautiful equations, my field equations of general relativity, and I added this extra term to make them say what I wanted them to say. The cosmological constant allowed for a static universe. It gave me the answer I was looking for. Problem solved, crisis averted, but something felt wrong. Deep down, even as I published the paper, I knew I had made a choice based on fear, not on truth. I had bent my mathematics to match my beliefs, rather than letting my beliefs follow the mathematics. And in science, that is a dangerous thing to do. That is how you miss the truth. That is how you let your assumptions blind you to reality. For the next 12 years, I lived with this uneasy feeling. My theory worked. It gave me a static universe, but it felt artificial, forced, like I had patched a crack in a wall rather than fixing the foundation. Other physicists began exploring my equations, looking for other solutions. Some of them, like Alexander Friedmann and Georges Lemaitre, found solutions that allowed for an expanding universe. But I dismissed their work. I clung to my static universe. I refused to let go of what I believed. Then, in 1929, something extraordinary happened. An astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, made a discovery that changed everything. He was studying distant galaxies, measuring their light with the most powerful telescope in the world, trying to understand how fast they were moving relative to us. And what he found was shocking. Every galaxy he observed was moving away from us, not just a few, not just the nearby ones. Every single galaxy, in every direction, was racing outward into space. Their light was shifted toward the red end of the spectrum, a phenomenon we call redshift, which told us they were moving away. And the farther away a galaxy was, the faster it was moving. The universe was not standing still. It was expanding, growing, stretching outward like a balloon being inflated, carrying the galaxies along with it. When I heard this news, I traveled to California to meet Hubble, to see his data for myself, to look through his telescope, and witness this expanding universe with my own eyes. And when I did, I felt something I rarely felt. I felt foolish. My equations had told me the truth all along, back in 1915, before I added the cosmological constant. The universe is not static. It is dynamic, alive, moving, and I had ignored that truth because I was afraid of it. I had added the cosmological constant not because the mathematics required it, but because I wanted the universe to behave in a way that made me comfortable, in a way that fit my preconceptions. I called it my biggest blunder, the greatest mistake of my scientific life. I should have trusted my equations. I should have had the courage to predict that the universe was expanding years before Hubble discovered it. I could have made one of the greatest predictions in the history of science, but instead I doubted myself. I let my assumptions, my fear of being wrong, cloud my vision. I let my ego get in the way of the truth, and I removed the cosmological constant from my equations. I admitted my mistake publicly. I told my colleagues I had been wrong. The universe was not static. There was no need for this artificial term I had invented. The cosmological constant was dead. Now, you might think this is where the story ends. Einstein made a mistake, admitted it, learned his lesson, and moved on. A cautionary tale about the dangers of letting your beliefs override your mathematics. But the universe, as I have learned again and again throughout my life, is far stranger than we imagine. And this story does not end with my mistake. It ends with a twist I never could have predicted, a twist that came long after I had left this world. Let me explain what we know now, decades after I first wrote those equations. For most of the 20th century, after Hubble's discovery, physicists assumed the expansion of the universe was slowing down. After all, gravity pulls everything together, so even though the universe is expanding, driven outward by the momentum of the Big Bang, we expected that expansion to gradually slow over time, like a ball thrown into the air that eventually slows down and falls back to the ground. The question was not whether the expansion was slowing, but how much it was slowing, and whether it would eventually stop and reverse, causing the universe to collapse back in on itself. But in the late 1990s, long after I had passed from this world, astronomers made another shocking discovery. They were studying Type Ia supernova, exploding stars that are so consistent in their brightness that we can use them as cosmic measuring sticks to determine distances across the universe. They measured the light from these distant explosions, trying to determine how much the universe's expansion had slowed over billions of years. And they found something unbelievable, something that made no sense. The expansion is not slowing down, it is speeding up. The universe is accelerating outward, faster and faster, driven by some mysterious force that pushes against gravity, that makes space itself expand at an ever increasing rate. This was so unexpected, so shocking, that the scientists who discovered it thought they had made a mistake. They checked their data again and again, but the evidence was clear. The universe's expansion is accelerating. And what do physicists call this mysterious force that drives the acceleration? They call it dark energy. And how do they describe it mathematically? They use the cosmological constant, the very same term I added to my equations in 1917, the very same term I called my biggest blunder, the very same term I removed in embarrassment after Hubble's discovery. It turns out that empty space does have a kind of pressure. It does push outward. Space itself carries energy, a tiny amount of energy in every cubic centimeter of the void, and this energy drives the expansion of the universe. I was not wrong to add the cosmological constant. I was only wrong about why I added it. I added it to make the universe static, but the real cosmological constant does the opposite. It makes the universe accelerate. Now, I must be honest with you. I do not know if this vindicates me or humbles me further. On one hand, the mathematics I invented, the cosmological constant I added to my equations, is now essential to understanding the universe. It is at the heart of modern cosmology. On the other hand, I added it for completely the wrong reasons. I was not guided by insight or intuition or a deep understanding of physics. I was guided by fear and assumption. I got the right answer, but for all the wrong reasons. And that, I think, is the real lesson of this story. Science is not about being right the first time. It is not about having perfect intuition or flawless logic. Science is about being willing to follow the evidence, even when it leads somewhere uncomfortable. It is about being brave enough to trust the mathematics, even when it contradicts your deepest beliefs, and it is about being humble enough to admit when you were wrong, to learn from your mistakes, to let go of your ego in pursuit of the truth. I was wrong in 1917. I let my assumptions control my equations instead of letting my equations reveal the truth. I was afraid to believe in a dynamic universe, so I forced my mathematics to give me a static one. But the universe did not care about my assumptions. It did not care about my fear. It expanded anyway, just as my original equations had predicted. And now, a century later, we know that space itself carries energy, that the cosmos is accelerating, that the future holds mysteries I could never have imagined. If I could go back and speak to my younger self, the man sitting in his study in 1917, staring at those equations and feeling afraid of what they were telling him, I would tell him this: trust the mathematics, do not add things to make reality comfortable, do not twist your theories to fit your expectations, let the universe speak for itself, and if it tells you something strange, something disturbing, something that challenges everything you believe, then listen, because that is when you are on the edge of discovery. That is when you are about to learn something true. But I would also tell him this: it is okay to make mistakes. It is okay to be wrong. What matters is not perfection. What matters is not getting everything right on the first try. What matters is curiosity. What matters is the courage to keep asking questions, to keep searching for truth, even when the truth makes you uncomfortable. What matters is the humility to admit when you were wrong, to learn, to grow, to move forward. The cosmological constant was my biggest blunder, but it was also a reminder that the universe is far more mysterious, far more beautiful, and far more surprising than any of us can imagine. And that is not something to fear, that is something to celebrate. That is what makes science worth doing. So the next time you look up at the night sky, remember this: the universe is not standing still, it is not frozen in time, it is expanding, accelerating, moving outward into the unknown at speeds we can barely comprehend, and we are part of that motion, part of that story. We are explorers in a cosmos that never stops surprising us, that never stops teaching us, that never stops showing us just how much we have yet to learn. And that, my friends, is the greatest adventure of all.